Hi, welcome to the next in our webinar series, which enables us to use our class time more efficiently. In this, we're going to look at centripetal force, why objects go in circles. By Isaac Newton's time in the mid-1600s, it was well known that the moon went around the Earth and the other planets went around the sun. Times of orbit were known, relative distances were known. However, the question was why. In his book Principia, written in lots of dense Latin, Newton postulated the answer to this. To come up with this, he first of all had the three laws of motion, which we covered in the first semester, centripetal force, which we're going to cover now, calculus, which broke things up into small parts, as well as the law of universal gravitation. All of this was set forth in his book, the Principia. To come up with this really big idea, Isaac Newton had to first postulate his three laws. He came up with this idea when he was at the age of 21. He published it when he was in his 40s. He did not have a lot of experimental apparatus, so for this he borrowed from other people's idea. The first law of inertia, objects at rest remain at rest. Galileo had done a series of experiments a few years before Newton's birth, where he showed that moving objects indeed stay in motion. This allowed for a moving Earth, because the Earth, it doesn't need anybody push it. The natural tendency of the Earth is to stay moving. The second law, F equals ma, came from this Johann Marcus Marci, personal physician to the Duke of Bohemia. He had borrowed some of the Duke's cannons and fired cannonballs one into another. He found that the acceleration was inversely proportional to mass. Or the other idea is that unbalanced forces change motion. The Earth wants to go in a straight line. The sun accelerates us by pulling us in a circle. The third idea, equal and opposite forces, just as the Earth pulls the moon down, the moon pulls the Earth up. We see this as evidence in the tides. Again, this was Newton's own idea. He was thinking that the Earth was pulling the apple down, therefore somehow the apple must be pulling the Earth up. Coming in this idea, Newton had this coming through this postulating this idea. His first one, inertia wants to take the moon in a straight line. However, gravity pulls us inward. Inertia, again, wants to take the moon in a straight line. It's going straight, as you can see by this red arrow. Gravity pulls us inward. Each one of these, the moon wants to go straight. Gravity pulls us in. The moon wants to go straight. Gravity pulls us in. The moon wants to go straight. They're straight. Gravity keeps pulling us in. A prettier version of this is right over here. The net result of this is a circle. Newton had to break it down into tiny little parts, hence calculus, to talk about how this works. But he came up with the idea that all mass attracts other mass. It's a non-balance or a net force acting on the moon. So we can say over here, the force of gravity of the moon and the Earth are equal and opposite. Nothing to balance them out. He called this centripetal force, meaning center seeking, center walking, just as we have a pedestrian is one who walks. So we can think about this. Fg, gravity in this case, is providing the centripetal force, the center walking force in Newton's words, or center seeking. From this, moving objects naturally want to travel in a straight line at constant speed. We can think about this again, the first law. The second law was an unbalanced force, hence gravity, causes there to be a change in speed or direction. Therefore, when it's moving in a circle, there's net force, and we call the special net force that moves us in a circle centripetal force. Because it is a net force, some combination of forces must cause it. Uniform circular motion means the object is moving in a complete circle, and it's perfectly uniform in terms of force. Newton's second law is about acceleration and a change of velocity. If an object changes either speed or direction, there is acceleration. Moving in a circle, our direction is continually changing. Therefore, we have to distinguish what type of acceleration we're dealing with. What we studied during the first semester was tangential acceleration. It's a change in speed. If we have a forward velocity, tangential acceleration is the component of acceleration parallel to our velocity. Centripetal acceleration, on the other hand, is a change in direction. If our velocity is forward, our acceleration, centripetal acceleration, is perpendicular to the velocity. This will cause it to change its direction. This is beginning to sound quite repetitive. However, when we move in a circle, linear velocity is constantly changing direction. We would like to qualify this and quantify it. So, as we look over here, we'll take the v2 vector over here, and I've simply sketched it out. Now, if we recall, a change in velocity is v2 minus v1. So quite conveniently down here, I've drawn out the negative of the v1 vector. This v1 was how fast it was going. A short time later, it has changed velocity to v2. My change in velocity, which gives me my acceleration, as we can see, we have an inward directed change in velocity. So my acceleration is inward. It takes some calculus to derive this, or there's an algebraic solution to it as well. But numerically, the centripetal acceleration we can quantify as v squared divided by r. I will not delve into the derivation here. However, you may look online for this derivation or ask me if you have dying curiosity. But if we're going twice as quickly around a circle, our acceleration will be 4 times as great. If the radius of the circle is twice as much, the acceleration is only half as much. A lot of explanations in practical life for this. Because objects moving in a circle are changing in velocity, there's acceleration and hence a net force. The key thing to remember, the centripetal force is nothing more than a very special case of the net force. Anything that can provide a net force can provide centripetal force. There's no centripetal force in and of itself. So, in this case, we can think about a ball moves in a circle. Tension in the rope pulls it inward. The Earth goes around the sun. Gravity is an unbalanced force, nothing connecting the Earth and the sun. So gravity's unbalanced, pulls it inward. Friction moves your car in a circle. We have to remember it's an inward directed net force. Quantifying this, as our equations have magically appeared, we see centripetal force is caused by some combination of forces. First set of equations right over here. The second set, we substituting in F net equals ma. Centripetal force, we'll just call it AC, FC. So we again can see some equations that we can use. Key thing to remember, centripetal force, inward directed net force, causes an object to accelerate, move in a circle. Tomorrow, we'll explore this in a class lab where we look at the qualitatively of what provides the net force, and then we'll look at quantitatively applying that in a subsequent lab. Thank you very much.